Hi, everyone. My name is Ekua Beneman. I'm a rising junior biochemistry major and mathematics minor at the illustrious Spelman College. And this summer, I had the honor of conducting research on catalytic living ring opening metathesis polymerization, otherwise known as ROMP, in the Johnson lab. In this presentation, we will be going through an intro or background of ROMP, the experiment and the synthesis, and the results and conclusion or discussion in the end. So ROMP is defined as polymerization driven by the relief of the ring strain of cyclic olefins to form polymers. And I'll just run through an example of what that would normally look like. So we have a cyclopentene ring and it opens up at the pi bond and it continues linking, and this is what it should look like, but this is how it's normally drawn. I also have a picture of Grubb's third generation catalyst because this is the catalyst that we keep the same and use through all of our experiments this summer. So in general, we use Norbornene derivatives for ROMP because they can be used in a living fashion, which means they allow fast and complete initiation, and they allow linear degree of polymerization. So the amount of monomers used to make a polymer will be linear to the amount of monomer that we began with. And the dispersity of the polymer or the distribution of length of polymer chains are very similar. Traditionally in the Johnson lab, where they use what we call traditional living ROMP. So one catalyst molecule per polymer chain, and there are high amounts of metal in the final product. But this summer, we worked on catalytic living ROMP, which produces more polymers with each catalyst, and it lowers the amount of metal in the final product. So the overview of the synthetic route is pretty simple. We purchase beta-bromosterine. It's commercially available as a mixture of isomers. So we isomerize it and use the trans, and we add a cyclic olefin, which are also commercially available. So something like the cyclopentene that I was talking about earlier. And we conduct a Heck reaction, which is in short a palladium cross-coupling reaction. And we end up with the chain transfer agent, depending on what N is. And in our case, it is 1, 3, and 4. So we synthesized chain transfer agent 5 with the cyclopentene on the end, but we just abbreviated it and called it CTA5. So we made 5, 7, and 8. And we used Momni, which is our norbornene, and we added our Grubb's third, our bromopyridine catalyst. And then with Momni as our norbornene, we conducted various experiments with chain transfer agent 5, 7, and 8. And we had chloroform as the solvent. And we ROMPed overnight and we created the polymer and we had 95% conversion. We also conducted ROMP with the ENDO as the monomer and Grubb's third, but we only used chain transfer agent number 5. So we had chloroform as the solvent and we ROMPed overnight. And we used the ENDO norbornene because it's known to be slow, so it allows batch ROMP, and we're able to let it sit overnight, but it's also amendable to standard modification conditions, meaning that it's able to withstand harsher conditions. Our results in the end, we have 2 controls, a red and a green. And we saw that chain transfer agent number 5 was the most efficient. It works really well in initiating new chains. And we're going to say it's because of the same molecular weight as the control 30, and the peak is more broad. And with the endo monomer, it works to some extent, but it's not as efficient as it was with Momni. And I would like to take this time to acknowledge everyone that helped me get to where I am.